for capillary absorption? Just draw a scheme to see how can you measure absorption. You said weight gain, that's a good idea. How are you going to measure the weight gain? Ideally, I would like to convert all of you guys into instrument developers, instrument manufacturers. So here we go. Here's your chance. Take a piece of paper and draw it. See how can you measure absorption. Does a wet material absorb anything? A wet material, completely wet material. It's unlikely. By that stage, it'll more be diffusion rather than absorption. So the prerequisite is the concrete should be dry. So you take a concrete, you dry it, and you put it into a moist environment or water environment, and then you measure the weight change. Right? That's it. So draw it. How would the test look like? So would the test look like a beaker with water? I'm going to put my concrete in here. That was a dry concrete. I put it at time 0. T1, T2, Tx. Okay? And I plot that and I should see the moisture build up or the weight gain. Okay, so this is the weight. Okay? Is that good? That's it. It's really not complex. Testing is not complex. It is complex, however, to put a unit to it. This is okay. Unit is fine and defined T in days. Yeah? What is the unit for that? Milligram. If you look at it, let's say you get change, which is in milligram, divided by time in days equal to y. You get a value of y, which is in milligrams per days. Yeah? What does that tell you? Does that milligram per days tell you anything about the concrete? For a surface area? You need to convert the rate of absorption to, because you're still testing the site. Your test is to go back to the site, right? So you took a core from the site, you tested it out, you got milligrams per days. How do you go back to the site to say that milligrams per days is equivalent to this much of water ingress onto the structure? So you need a way of relating that to the surface area. Okay? So for a test like that, the entire surface is taking part. Okay? Some of it, the water is coming to the gravity. Some of it, the water is going against the gravity. It will have a bearing, however small. And some of it, it's neither from both sides. So the surface area in this case could be the total surface area of the cube, if it's a cube. Happy enough? And that gives you the dimension of meter square. Okay? And then you have a better way of converting. You can say for a meter square, this will be the milligrams of water at a given time. Which when you convert it, you can get the moisture content. Does that make sense? You need to have that much amount of information in order to progress, to expand the days into years. That's your ultimate aim. Your ultimate aim is to say in 50 years, this will be the moisture content at my steel surface. And that's what you're going, isn't it? So you need to have this much amount of information captured. Happy enough? Okay. the observation needs to have a particular behavior, because if it doesn't, you can't get the slope. This is essentially a slope. That divided by that, you're getting the slope. So which means there has to be a sloping portion. Okay, that is easier. If it doesn't have a sloping portion, if it has a very curvature area, you can still get a non-linear slope. Okay, becomes a bit more complex, but it depends on the behavior. Okay, so the next thing to do is to observe the behavior. Okay, needless to say, if you get a value like that, you can always compare concrete A against concrete B against concrete C, concrete D. So comparison wise, any test that you develop will work. That's given. Okay. I converted you in the test developer. So that's all it takes for durability assessment. You need to be able to get the unit correct. You need to be able to observe the behavior. And for comparison, any of your tests, if it's systematic, it will work as long as it follows the observation. Okay. If one concrete does that and the other concrete does that, clearly the observation has gone away. Therefore, there's no correlation. You can't compare. You happy enough with that part? So, if you look at the flow into square root of time, then the slope of that is defined mathematically as sorptivity. Okay? How are you going to get the flow? So, a couple of things that they're doing in this test. There is an ISAT test. It's called Initial Surface Absorption Test. There's European proceedings on this kind of test. EN 12390. There's a British standard on that as well. I'm sure there may be an Indian version of it as well. Sorptivity. It's a very common test for a lot of other areas. But they need a surface area very clearly defined. So in this case, what they've done is exactly like this, but they put the concrete this way so that the water can go through only this surface. And they very likely have sealed these two surfaces, which means the surface area is the minimum area that's exposed. So whatever flow of millimeter of liquid, or milligrams of liquid, or volume of liquid is for that surface area for that time. So they get the flow quite easily. Okay, that is designed as a unidirectional flow. Just waterproof the two sides. That's it. Why did they not coat the top? This is the cast surface, so they haven't coated. They did not coat the top surface. Why? This is concrete. Capillary rise will be millimeters. When you have water rising up, does it displace anything else? Vapor or water is being displaced. You need to have a space for them to escape. If you don't, it'll stop the capillary from. You compress the air for a certain time, and then it'll stop. And this is why I was saying that in the test, you need to be very clear of the observations. Okay? So they would have observed that if you put something on the top, it'll either pop off or it is starting to prevent things. Okay? So that level of observation is very critical. So there you go. Sorptivity is obtained. Our challenge from this point, this test is standardized. It's been there for a while. So quite a lot of people use it. There's a European standard on it now. It's a very clearly defined standard. So for those who are looking to use it, can refer to the European standard. But our issue was these. That means you need to remove cores from the structure to test them. You need to dry them, you need to test them. We prefer non-destructive testing. So we wanted to evolve from that to something that you can apply on the surface. And this is the other air permeability test. Okay? So for air permeability, you put the concrete in the middle. You have one gas here probably oxygen at a different pressure, and you have a reverse gas pressure, probably nitrogen at the same pressure. And we're looking then at the flow rate of decay of one over the other gas, and that tells us how much is the gas pressure through flow of gas through the concrete surface area per time. So all of it is flow per time for a given surface area. From that, we then decided we will use a surface mount device. Same concept as here, but instead of having the water bath to be the mount, we limited the water bath to a very small region of the large concrete surface. So this is your water, and that's your concrete. Okay? When we manage to do that, this is the fixing bolt. So it's fixed onto the surface. It then will let the moisture go into the concrete. If we have a way of measuring the water that's leaving, we then get the rate. It's quite easy. The tricky part is, where does it go? It goes everywhere. Okay? But that's a bit of mathematics. But water is not anything, if you tell it to go, it doesn't necessarily have to go. So you need to create a small pressure head here for it to go. So for absorption or sorptivity test, we put a very small pressure, 0.5 bar, I think. I think it's 0.5 bar. I need to look up it. 0.5 bar, okay. So 0.5 bar, this is the reservoir, and that's the surface that attached to the concrete using one of those rings. And there's a small pressure built up between the reservoir and here, and there's a tiny syringe sitting inside. It's a medical syringe, and it can tell us the rate of flow of water in microliters. So it's very, very, very small precision tool. If you ever bought one of these instruments, this is one of the most complex instruments of its scale. If you lift it, you will see hundreds of pipes and loads of pressure transducers inside, because it is measuring everything in a very fine level. And it pushes so that's the first thing it does. The reason it's a complex instrument is because that's designed to do three things. Water absorption is one, water pressure test is the other one, and the air pressure test is the third one. So this test can do 3 tests. Not in one go. The sequence is very critical, okay? You cannot do wet concrete. You can only do absorption on a dry concrete. So don't do the water test first and then progress to absorption. So absorption have to be done before the water permeability test is carried out. Air permeability is the same scale. It has to be dry concrete. So what we do is we test the air permeability first. We let the air pressure dissipate. We let it open. And then we do the absorption test. Then we do the water permeability test. Okay? The manual tells you how exactly to do it. So any test that you buy, if it has more than one capability, read very carefully how to do the sequences. The output will be in the display. It calculates the sorptivity coefficient for you, but it also gives you the values to plot on the graph. This is an older version. I think the newer version have that in here. Technology has changed dramatically. So the display is on the top, and there's a USB pen that you can collect the information. Universities only get involved in the prototype and the concept, and after that we take a step back and let whoever buys it to run with it. So it's sold commercially by a company called Amphora, and all the developments thereafter is Amphora's. As far as I know, they have a digital display on the top which tells you the information. I've seen the torrent test as well. That has a very similar system as this, has a 2-unit system, but it doesn't need a fixer. It's 2 vacuum cells. So the first vacuum cell will keep the inner vacuum cells on the surface quite easily, and the inner vacuum cell will absorb or send the air into it. So it's a very simple test. And Roberto is a very active researcher. So he still travels. He's quite a unique character. Any more questions on that?
So which would be the best way to measure the permeability? Because when we measure the gas permeability or the water permeability with the pressure gauge, there is always a possibility that the cells which we have, the gaskets, they tend to not to be in place. Because of which most of the times the results which we want to test,
Okay.
we don't get the correct values.
Okay. I'll come to that in a minute. Any questions? Anyone else? Any questions?
And one more thing, the sorptivity, the graph, slope by area,
Yeah.
it is square root of time, right?
Yeah. That's to do with the behavior. So certain behavior may not have a linear relationship between time and the flow. In that case, when you convert that into square root, it will become linear. It's much easier to handle. If you want to handle it with the time, you can, but you need to use nonlinear equations. Just for that factor. Up until 1990s, linear is the easy thing that you can do by hand calculation. Nonlinear means you needed a computer and a bit more coding, but technology has changed tremendously. I can program the nonlinear stuff, which you will do, in the computer in Excel file quite easily. Any more questions? I'm going to ask, what are the limitations of the test? Yes, it is developed in Queen's University. That aside, what are the limitations of the tests? Or what are the limitations of such surface testing?
Creating the same environment.
You're testing on the surface. Surface will have different environments. If the environment is moist, above 80%, won't work. It can't work because you can't compress water. So you'll have to dry the surface if it's less than 80. If it's more than 80% humidity, you'll either need to find a different way of testing it or you'll need to dry it. First limitation. What's the next limitation? By the time I listed all the limitations, you will actually develop your own test anyway. That's the idea. I'm a researcher, I'm not a salesperson. Go ahead. What's the other one? The flow that it measures, I did say it's microliters precision. It's a very small flow. It's a very small area. That's a 75 mil opening diameter. This is a 50 mil opening. It's a very small area in the large structure. You are defining everything to that tiny area. And a very tiny flow. Tiny flows because the water flow is tiny. It's just the number of years that accumulates. So scaling up from that to the whole thing is challenging, but that's challenging for anything. The problem with this test is that it's trying to push water through a very fine device. Okay? If you manage to get any dirt in the system, you are snookered because there's a lot of microfine parts. There's a lot of valves in the system as well. I think the new design accommodated a lot of those changes, but reality is it is very clean clinical instruments. So if you are looking for a bit more rough site, my suggestion, take a core and bring it to the lab. Okay? Site variability is something you will need to consider. Without site variability, you can't interpret the data. So my suggestion will be to look at the site using one of those typical NDT tests. I suggest electrical resistivity because it's much more easier. And then decide which area you're going to test. Test that area and then approximate everything back to the site. We can look at that. I will show you an example. The other thing is it's 50 mil on the surface or 75 mil on the surface, the depth to which it will measure is also small because the pressure that it can apply is small. So if that surface skin of concrete has micro cracking, plastic shrinkage cracking, or any other cracking, the results will be all over the show. Probably will answer the question you were asking earlier, that the flow is not comparable between the different tests. The reason is microcracks will affect each kind of surface bound test much more than a core. So if you expect microcracks on the surface, on the structure, on the surface, do not go for a surface bound test. Always have a laboratory test in comparison. Because laboratory samples you can test thicker sample, so you're avoiding the skin effect, you're taking the whole bulk. So that might help to reduce the variability. And ultimately the variability is a property of concrete, and that's what you're measuring. Any more limitations? I don't think M4 would like me to say any more limitations, but I mean, limitations are the same for any instrument in the market at the moment, okay? And limitations are what people use to derive the next instruments. I openly believe in conveying the limitations so that one of the researchers will create a new instrument, preferably a cheaper instrument. Because as it gets more and more cheaper and affordable, not cheaper, then the test will become common. Okay? Anybody working in the chloride or absorption area, that test is critical. It's so easy to do. Find a facility where you can do that. Probably you can do that in your own shed in the house, or you can do that in the lab. A similar test is available commercially, and it's for the ISAT. I think if you Google ISAT, you should be able to get that. So you have a concrete, and they will ask you to drill a hole, and on top of that they will put a test tube which has striations in it. You put water in it, and then you measure the drop in water after a certain time. Okay, it's a standard procedure. It's very simple. You can drill a 20 mil hole, diameter hole, up to a certain depth, and you can do that in several locations. It'll look a bit funny on the structure, but 20 mil hole is not structurally critical. Okay, so there are other tests available as well. Okay, happy enough? What comes next? Anyway, I've explained that. So this test, we were developing it also for surface treatment, was getting very popular at a certain time. So we were looking at that test to see, can we assess the surface treatment? Yes and no. Air pressure and water pressure might work for surface treatment. Absorption properties will be completely different if you're coating. It's not sensitive, I think. You get different kind of results. Any of those tests will give you very similar results. And so this is for freeze thaw scaling. Due to freeze thaw, scaling is the falling apart of the particles. And as the permeability increases, you would expect the scaling to increase. That's what you're seeing by the linear curve. Corrosion initiation time in weeks will drop as the sorptivity index increases. Sorptivity index increasing means it's very connected pore system. So you should expect corrosion initiation to happen much faster. These are bad concretes, these are good concretes. A cover has a large role to play, so don't expect every cover to have the same relationship. Don't expect every concrete to have the same relationship. Any questions? You can, okay, go ahead.
Can you explain once?
Oh, okay. So what we looked at is we looked at a paddle beam, a beam which had the macro cell arrangement. You have the anodes and the cathode and the electrical arrangement. And we tested the sorptivity of that concrete. What we found out is if the cover is 25 mil, okay, you get a relationship like that.